section 7.6, we're going to predict the structures of small molecules using valence shell electron pair repulsion, VSEPR theory. We're going to explain the concepts of polar covalent bonds and molecular polarity, and we're going to assess the polarity of a molecule based on its bonding and structure. So with the Lewis models, we've been looking at two-dimensional representations of molecules, but molecules are three-dimensional objects. So in order to fully represent the molecular structure, we must be able to describe the bond distances, bond angles, and relative arrangements in three-dimensional space. So bond angle. If we look at our planar acetone down here, the bond angle is going to be the angle between any two bonds, right? So this is a bond angle. There's going to be a bond angle here, and there's going to be one here. This one happens to be about 118 degrees. And then we have our bond distance. This is the distance between the center of the two nuclei on these atoms. And here you can see this represented using 1.21 angstroms. We usually use angstroms or picometers, where an angstrom is 10 to the minus 10 meters, or a picometer is 10 to the minus 12 meters. Valence shell electron pair repulsion theory, VSEPR theory, enables us to predict the molecular structure, including approximate bond angles around a central atom. Predictions are based on the number of bonds and lone electron pairs in its Lewis structure. VSEPR assumes that electrons in a valence shell will arrange themselves in order to minimize the repulsion between electrons. And it does that by putting them as far away from one another as possible. VSEPR is usually able to predict the correct arrangements of the molecules, and it does this only by taking into account the electron-electron repulsion. So the way that the nuclei repel each other, the way that the electrons attract to the nuclei, these are not considered in the VSEPR theory. Let's look at an example. The Lewis structure of this molecule predicts that beryllium will have two bonds and no lone pairs. In order to separate the electron-rich fluorine atoms, VSEPR predicts that we're going to have a linear arrangement with 180 degrees between them. In practice, we would see that this is actually true. We're just going to place these two fluorines as far apart as possible. Here we have a very important table that you guys are going to have to come back to, where we describe what's going to happen as we add different regions of electron density around central points. So remember that these could be atoms or they could be lone pairs. And what's going to happen, so when we have two regions, we get a linear structure. When we got three regions, we're going to get this trigonal planar. So that's it, all on the same plane. Then once we have four, now we're getting into three-dimensional structures, such as the tetrahedron here, where this hydrogen is in the back, and this one is in the front. If you guys are having kind of trouble picturing any of these, I suggest you go and Google tetrahedron, which is a shape, and you'll see exactly what this is here. If you have trigonal bipyramidal, you're going to wind up with this kind of structure, which is pretty unique, because if you look here, there's a difference between the bond angles here. So any one of these three along this periphery here are 90 degrees apart from the top ones and 120 degrees apart from one another, whereas these top ones and the bottom one here are 90 degrees away from all the others. Okay, so these ones here at the periphery with 120 degrees between them, those are called equatorial positions. And the ones on the top and the bottom are called the axial positions. And we're going to see in a moment that that can be kind of important. Once we get up to 6 regions, we're going to get this octahedron shape, where all of our atoms, electron regions, are 90 degrees apart. Molecular structure is a geometry of a molecule that depicts all the atoms in 3D, but electron pair geometry is the 3D geometry that includes all of the atoms and all of the lone pairs. So here we can see that this is an electron pair geometry because it's got the lone pair described there, Whereas here, we're omitting the lone pair and we're only showing these atoms and how they are arranged. I mentioned before that we use these wedges here to depict a hydrogen that's coming out of the plane of the paper, or the screen in this case, and we're going to use these dash lines to depict hydrogens that are inside of the plane facing away from us. You're going to see this kind of notation used extensively in organic chemistry if you continue to go on. So some regions of electron density repel one another to a greater extent. So lone pairs and lone pairs, so two lone pairs interacting with one another are going to repel each other more than a lone pair would with a bonding pair. And bonding pair interactions are going to be even less. Okay, so this leads some regions of electrons to occupy more space than others. So we're going to think of lone pair as being a big space. It's a big thing that's occupying a lot of space. Triple bonds are a little less, double bonds a little less, single bonds being taking up the least amount of space. And the regions that occupy more space will push neighboring regions, leading to slight variations in the bond angles. So let's take a look at that. In this example here, we have our trigonal planar here, and everything's 120 degrees apart, giving us 360 degrees all the way around. But when we put in this lone pair, we're going to expect that these two are going to get squished together a little bit, and we're going to have less than 120 degrees. Similar here, in a proper tetrahedron, they're all 109 degrees apart. However, when we put the lone pair here, it pushes all three of these down a little bit, and we're going to get less than 109 degrees here. Again, if we put two lone pairs here, they're going to really repel each other a lot. That's going to push these two much closer together. We're going to expect that we're going to get much less than 109 degrees. This would be this situation in something like, say, water. Here we have our trigonal bipyramidal, and you can see that we get our 120 degrees here and our 90 between the equatorial and axial points atoms. When we put in a lone pair, it starts to push these guys closer together, so that these now have less than 120 degrees apart, and this is even less than 90 degrees. And this leads to a very asymmetrical shape that we call the seahorse or seesaw. If we put in two lone pairs, we're going to see that we actually wind up with something that has 90 degrees apart from all of these. And then if we put in a third lone pair, we're going to arrange these two 180 degrees apart from each other. Notice that as we added these lone pairs, they always went into the equatorial positions, and they always will. So that's an important thing to note, that these positions are not the same when we're dealing with the trigonal bipyramidal arrangement. And that's reiterated here. And here we can picture the axial versus the equatorial positions. The Vesper procedure. The first thing we're going to do is we're going to write out the Lewis structure of a molecular polyatomic ion. Second, we're going to count the numbers of electron density, the lone pairs and bonds around the central atom. A single, double, or triple bond counts as one region of electron density in this case. Third, we're going to identify the electron pair geometry based on the number of regions of electron density. And you're going to do that by going back to this table in conjunction with this table here. Fourth, we're going to use the number of lone pairs to determine the molecular structure. If more than one arrangement of lone pairs and chemical bonds is possible, we're going to choose the one that will minimize repulsions. In trigonal bipyramidal arrangements, repulsion is minimized when every lone pair is in an equatorial position. In an octahedral arrangement, the two lone pairs, repulsion is minimized when the lone pairs are on opposite sides of the central atom. So molecular polarity and dipole moments. So we saw earlier with our formal charge that pure covalent bonds can lead to partial charges, which we can abbreviate with this sigma plus, meaning a partial positive charge, or sigma minus, a partial negative charge on the bonding atoms. This separation of charge gives rise to a bond dipole moment. A dipole moment is a vector. Vectors are essentially mathematical representations of an arrow with a direction and a magnitude. Our dipole moment vectors are going to point towards the more electronegative bonding atom. The magnitude of the vector, given by mu, is dependent on the magnitude of the partial charges and the distance between the charges. So we can see that as the distance increases, the dipole moment is going to increase. We pull those two charges apart, inputting energy, which is going to yield a higher dipole moment. And when the partial charges are larger, we're going to get a higher dipole moment. What Q here is mathematically would be the difference between the partial charges. If you subtracted the positive one, or if you subtracted the negative one from the positive one. Dipoles with large magnitude are written as vectors of greater length. So here we can see we have carbon and hydrogen. There's not a huge difference between them, so we get a smaller vector. And by difference, I mean the difference in their electronegativity. Here we have boron and fluorine. There's a very large difference in their electronegativity. We get a larger dipole moment. So for diatomic molecules like we just saw, it's pretty easy. We only have one bond, okay? And the polarity of the whole molecule is described by that single dipole moment. Molecules with a net non-zero dipole moment are called polar molecules. So we're going to see that we can combine those bond dipole moments together to get a molecular dipole moment. When that molecular dipole moment is not zero, we get a polar molecule. And to do that, we have to sum our vectors. So let's talk about what vector summation looks like. You guys may have seen this in physics. If I have vector A and I have vector B, the sum of them is going to be vector C. How do I know that the sum is C? Well, if I put these two heads to tails, then it's going to start off at the origin of the C, and it's going to end at C, okay? So what we're seeing here is that if I move B up so that its tail meets A's head and then come over, I get C, and that it doesn't matter if I move B up or if I move A over. Both of those arrangements are going to yield the same vector C. We can do it with more than that, more vectors. So here we have F, D, and E. Their summation is G. And any way that I want to arrange those, heads to tails, I'm still going to wind up with G. So sometimes these bond dipole moments can cancel. In this case where we have symmetry and they're opposed to each other, they're going to cancel each other out, and the whole overall dipole moment for this molecule is going to be 0. But sometimes they don't. So in the case of water, we have a dipole moment heading here towards oxygen, one heading here. If I picture moving this over, such that it was heads and tails with this guy, I'm going to get this resulting dipole moment, which is the dipole moment for the whole molecule. Sometimes the dipoles can oppose each other but just have different magnitudes, in which case you're going to wind up with a dipole moment that's smaller than this one, but you're still going to have an overall dipole moment for the molecule. Okay, so polar molecules are going to align themselves to external magnetic fields. Polar solvents will better dissolve polar solutes, okay? So this is the like dissolves like sort of thing. Nonpolar solvents are going to dissolve nonpolar solutes. Polar solvents are going to dissolve polar solutes. Here we can picture this electric field thing. So we have these molecules, they're floating around, and they're just arranging themselves in any old way, you know, whichever way they feel like at any moment. They're moving, and these arrangements are changing all the time. Once we apply that external electric field, though, all of the partial negative charges are going to face the positive end here, this positive plate, and all of the partial positive charges are going to face this negative plate, and we get a very coherent, aligned situation. This is only going to happen, though, in the gas phase or in a liquid phase, where these molecules are free to move about and not trapped in a solid lattice.